Welcome back. In this video, we're going to look at examples of determining the convergence of telescoping series. Let's get to it. All right, so here's our first series. We have the sum from n equals 1 to infinity of 1 divided by n plus 2 minus 1 divided by n plus 3. And so what we want to do to determine the convergence of this series is first identify if it is a telescoping series. And if we can say that about this series, we will be able to determine its convergence pretty easily. And so here's what you need to know about the convergence of a telescoping series. If you can identify that a given series is of this form, where your terms are going to collapse or telescope because we have negative and positive versions of them, right? We have negative a sub 2, which cancels out with positive a sub 2. Negative a sub 3 cancels out with positive a sub 3, and this would continue on for all of these terms in the middle. And if we were to look at the nth partial sum, we would just be left with a sub 1 and a sub n plus 1, the first term and the last term. And so then from that partial sum, we could find the sum of our series by taking the limit of the partial sum. And if we did that, the limit of a sub 1 would just be a sub 1 since it's a constant, but then we would have the limit of a sub n plus 1. Now, if that limit exists, then we would say that the series converges to the value that results from a sub 1 minus that limit. That will be the sum S of our series. However, if that limit does not exist, meaning it diverges, then the series also diverges. Okay, so all of this only applies to a series that is a telescoping series of this form. And so let's go back to our example. Let's take a look at the nth partial sum of our series and see if we can identify that it is a telescoping series. So we'll start with our first term, a sub 1. What we're going to do is plug in 1 for n in this expression. So we have 1 divided by 1 plus 2, and 1 plus 2 is 3, so we have 1/3. And then we will subtract 1 divided by 1 plus 4, which is 1/4, so we have 1/4. Then we will add this to a sub 2. And so if we plug 2 in for n, we will have 1 divided by 2 plus 2, which is 1/4. And then we will subtract 1 divided by 2 plus 3, which is 5, so we have 1/5. All right, and now let's do one more term. Let's do a sub 3, where n is equal to 3. So we'll have 1 divided by 3 plus 2. That's going to be 1/5. And then we will subtract 1 divided by 3 plus 3, which is 1/6. And now already we can start to see that we have a telescoping series of the right form. We have 1/3 minus 1/4, but then we have a positive 1/4, then minus 1/5, and then a positive 1/5. This negative 1/4 and this positive 1/4 are going to cancel out, just like these two 1/5s will cancel out because one is negative and one is positive. And so this would continue on, but now let's skip ahead towards our nth term. We're first going to look at the a sub n minus 1 term. So if n is equal to n minus 1, we have 1 divided by n minus 1 plus 2. So if we have n minus 1 plus 2, negative 1 plus 2 is positive 1. So that denominator will be n plus 1. So we will have 1 divided by n plus 1 minus 1 divided by n minus 1 plus 3. And so n minus 1 plus 3, negative 1 plus 3 will be positive 2. And so that denominator will be n plus 2. So we have 1 divided by n plus 2, and then we will add that to our last term of a sub n, right? The nth partial sum adds up all the terms to a sub n. And so when n is equal to n, we just have this expression right here, 1 divided by n plus 2 minus 1 divided by n plus 3. And so that's what I'll write down, 1 divided by n plus 2 minus 1 divided by n plus 3. Okay, so now looking at the terms of our nth partial sum, I can see that this negative 1/4 will cancel out with this positive 1/4. This negative 1/5 will cancel out with this positive 1/5. This negative 1/6 will cancel out with a positive 1/6 in the next term. This 1 divided by n plus 1 will cancel out with a negative 1 divided by n plus 1 in the previous term that we don't have written there, but it would cancel out if we're following the pattern here. And then this negative 1 divided by n plus 2 will cancel out with this positive 1 divided by n plus 2. And so what that leaves us with is this positive 1/3 from our first term, a sub 1, and this negative 1 divided by n plus 3 from our last term, a sub n. And so what we find is that s sub n is just going to be equal to 1/3 minus 1 divided by n plus 3. The first term minus the last term. Okay, and so because this series is a telescoping series where all of those middle terms are going to cancel out or collapse, we are able to conclude that the nth partial sum will just be equal to the first part of our first term minus the second part of the last term. Or you could just view it as the first term minus the last term if you view each individual fraction as a term. Okay, and so if I clean up my work here, we can determine the convergence of our telescoping series by taking the limit as n approaches infinity of our nth partial sum. And so if we do that, we will have that the sum of the series will be equal to 1/3 minus the limit as n approaches infinity of 1 divided by n plus 3. All right, now if we look at this expression as n approaches infinity, 1 divided by n plus 3, this n is going to approach infinity, and so as that n gets larger, we're just adding 3 to it, so it's still becoming larger, and so that whole denominator is increasing towards infinity, and so we have 1 divided by infinity, or an increasing value, and when you have a fixed value divided by an infinite value, or an increasing value, that expression is going to head towards 0. And so we have that s is equal to 1/3 minus 0, which means that s is equal to 1/3. And so we find that the sum of our telescoping series is 1/3, which means that the series converges to 1/3. All right, and so that's how we can determine the convergence of a telescoping series. Let's look at another example. Okay, so here's our next series. We have the sum from n equals 1 to infinity of 2 divided by 4 times n squared minus 1. Now at first this doesn't seem like it's going to be a telescoping series, but let's look at some of the terms of the series before we make any conclusions. Let's start with n equals 1. We're going to have 2 divided by 4 times 1 squared minus 1. Then we'll add that to the next term, where we have n is equal to 2. So we'll have 2 divided by 4 times 2 squared minus 1. And then let's do one more with n is equal to 3. So we'll have 2 divided by 4 times 3 squared minus 1. And of course, that would continue on from there. Now, if we simplify, this will be equal to 2 divided by 4 times 1 squared. 1 squared is 1 times 4 is 4. 4 minus 1 is 3. So we have 2/3. And then we'll add that to 2 divided by 4 times 2 squared minus 1. And 2 squared is 4. 4 times 4 is 16. Minus 1 is 15. So we have 2/15. And then we'll add that to 2 divided by 4 times 3 squared minus 1. Now 3 squared is 9. Times 4 is 36. Minus 1 is 35. So we have 2/35. And so then that would continue on from there. Now, by looking at the terms we have here, it doesn't really seem like this series is a telescoping series, right? None of these terms are collapsing or canceling out or telescoping, whatever you want to call that. They're all positive terms, and it seems like that's going to continue on like that forever. However, this is a telescoping series, but it's actually a telescoping series in disguise. What we can do is actually break up this rational expression into two separate rational expressions by using partial fraction decomposition, right? We have a denominator here that can be factored, and then we can split up the rational expression by using those factors with partial fractions. And so let's do that. Let me show you what happens when we break up this rational expression. But first we need to fully factor that denominator. So we have 2 divided by 4 times n squared minus 1. What we have here is a difference of squares, right? 4n squared is 2n squared, right? If you have 2n and you square it, that will be equal to 4 times n squared, because 2 squared is 4 and n squared is n squared. So we have 2n squared minus 1 squared, because 1 squared is 1. And so we can factor that difference of squares to be 2 divided by 2n minus 1 times 2n plus 1. Okay? And now that we have identified the two factors in our denominator, we can write out the partial fractions that we can break up this rational expression into. We're going to have one partial fraction for each of these factors, And note that both of them are linear factors, meaning we just have n to the first power. And so our partial fractions will look like this. We'll have a coefficient of a divided by the first factor of 2n minus 1, and then we'll add that to a second fraction where we have a coefficient of b divided by the second factor of 2n plus 1. And now what we want to do is set up an equation that will allow us to solve for a and b, and then we can rewrite our series with those partial fractions. And so the way we're going to do that is by setting this numerator equal to each of these coefficients multiplied by what they need to have in their denominator to have the common denominator, right? Because what we're saying here is that this fraction is equal to these two fractions. And so if we got a common denominator between these two fractions, it would be both of these factors multiplied together. Then we could say that this numerator must be equal to the numerator over here. And so what that's going to be is 2 will be equal to a times what factor it needs in its denominator to have the common denominator, which since it has 2n minus 1, it needs 2n plus 1. So we will have a times 2n plus 1, and we will add that to b times the factor that it needs in its denominator to have the common denominator. And so it has 2n plus 1, but it needs 2n minus 1, so we multiply b by 2n minus 1. And now this equation right here can be used to solve for a and b and complete our partial fractions. Now if I clean up my work here, what we can do to solve for a and b in this equation is pick a convenient value of n that will allow us to solve for each value. And so I want to start by solving for a, and so what value of n can we choose for this factor that will make this whole term 0? That's what I mean by a convenient value of n. It's going to make this term 0 so that we can solve for a and ignore b. And so what is going to make this factor equal to 0? Well, this term is going to have to be equal to 1, right? Because 1 minus 1 would be 0. And so what times 2 is equal to 1? Well, 2 times 1/2 will be 1. And so if we let n equal 1/2, watch what happens to our equation. We'll have 2 is equal to a times 2 times 1/2 plus 1 plus b times 2 times 1/2 minus 1. If we simplify, this will be equal to a times 1 plus 1, because 2 times 1/2 is 1, so we have 1 plus 1, and then we'll have plus b times 2 times 1/2, which is 1 minus 1. Now 1 minus 1 is 0, and 0 times b is 0, and so this is just going to become 0, and so we just have 2 is equal to a times 1 plus 1, which will allow us to solve for a. And so we have 2 is equal to a times 2, and then we could have plus 0, but we don't need to write that. And if we divide both sides by 2, we will find that a is equal to 1. All right, so now that we know what a is equal to, we now want to solve for b. And so we can do the same process again, but notice that if we made n negative 1/2, that will make this term become 0, right? Negative 1/2 times 2 will be negative 1, plus 1 will be 0. So if n is equal to negative 1/2, we will have 2 is equal to a times 2 times negative 1/2 plus 1 plus b times 2 times negative 1/2 minus 1. And so we'll have 2 is equal to a times negative 1 plus 1, right? 2 times negative 1/2 is negative 1, and negative 1 plus 1 is 0. And so this whole term just becomes 0. So I'm just going to rewrite that. This becomes 0. And so we just have 0 plus b times 2 times negative 1/2, which is a negative 1, and then we have minus 1. And so negative 1 minus 1 is negative 2. So we have 2 is equal to b times negative 2, and if we divide both sides by negative 2, that will give us that b is equal to negative 1. Okay, so now we know that a is equal to 1 and b is equal to negative 1. So if we replace those values in our partial fractions, a will become 1. So we have 1 divided by 2n minus 1. And then b will become negative 1. So we'll erase that, and we will have negative 1 divided by 2n plus 1. Now if we bring that negative out front, we can just subtract that fraction instead, and we have an equal expression. Okay? And so now we can rewrite this rational expression in our series with these two partial fractions. And so if I clean up my work, we will say that the series is equal to the sum from n equals 1 to infinity of 1 divided by 2n minus 1 minus 1 divided by 2n plus 1. And now we can look at the terms of this series and see if we can identify it as a telescoping series, and if we can, then we can determine the convergence of that series. And so I'll clean up my work again here. Now that we know that this series is equal to this series, let's look at the nth partial sum of our series and see if the terms are going to collapse. And so we'll start with our first term, a sub 1. If n is equal to 1, we have 1 divided by 2 times 1 minus 1. 2 times 1 is 2, minus 1 will be 1. So we have 1 divided by 1, which is just 1, minus 1 divided by 2 times 1 plus 1. 2 times 1 is 2, plus 1 is 3, so we're subtracting 1/3. Then we'll move on to our next term, a sub 2. And so if n is equal to 2, we have 1 divided by 2 times 2, which is 4, minus 1, which is 3. So we have 1/3. So I'll write down 1/3, minus 1 divided by 2 times 2, which is 4, plus 1, which is 5. So we have negative 1/5. So I'll write 1/5. Then let's work on the next term, a sub 3. And so when n is equal to 3, we have 1 divided by 2 times 3, which is 6, minus 1, which is 5, so we have 1/5. And then we will subtract 1 divided by 2 times 3, which is 6, plus 1, which is 7, and so we have 1/7. Now I'm going to stop there. We can already see that our terms are collapsing. We have negative 1/3 and positive 1/3, negative 1/5 and positive 1/5, and then this negative 7th is going to cancel out with the next term, where we will have a positive 1/7. And so since we can see that our terms are collapsing, let's skip ahead to our nth term. We're going to add this to a sub n, which will be 1 divided by 2n minus 1 minus 1 divided by 2n plus 1. That's just what we have up here. And so we know that since negative 1/3 and positive 1/3 will cancel out, negative 1/5 and positive 1/5 cancel out, negative 1/7 will cancel out with the next term, and then the first part of this term will cancel out with a term before it, and we're just going to be left with positive 1 and negative 1 divided by 2n plus 1. That is going to be our nth partial sum. So we will have s sub n is equal to 1 minus 1 divided by 2n plus 1. That is the nth partial sum of this telescoping series. And so now if we want to determine the convergence of our telescoping series, we will take the limit as n approaches infinity of our nth partial sum. And so if I clean up my work here, we will have that s, the sum of our series, will be equal to 1 minus the limit as n approaches infinity of 1 divided by 2n plus 1. All right, now what happens to this expression as n approaches infinity? Well, we have 2n plus 1 in the denominator, and so as this n approaches infinity, we have an increasing value times 2, which is still increasing, plus 1, which is still increasing, and so as n gets larger, this whole denominator will also get larger. So we have 1 divided by an increasing value, or a fixed value divided by an infinite value, and so we know as n approaches infinity, that this expression is going to approach 0. Whenever you have a fixed value divided by an increasing value, it's going to become 0. All right, so s is equal to 1 minus 0, which tells us that the sum of our series is equal to 1. All right, and so what we know is that our telescoping series converges to 1. All right, let's look at one more example for this video. All right, so here's the last series we're going to look at. We have the sum from n equals 1 to infinity of 2 divided by n squared plus 2 times n. All right, now similar to our previous example, this may not look like it's going to be a telescoping series because we don't have some fraction minus another fraction, but let's look at the first couple terms, and if it still doesn't look like a telescoping series, then we might need to use partial fractions again. And so if we look at the first term, a sub 1, where n is equal to 1, we'll have 2 divided by 1 squared plus 2 times 1. Then we'll add that to the next term, where n is equal to 2. So we'll have 2 divided by 2 squared plus 2 times 2. And then let's do one more, where n is equal to 3. So we'll have 2 divided by 3 squared plus 2 times 3. And then, of course, that would continue on from there. Now, if we simplify, this will be equal to 2 divided by 1 squared, which is 1, plus 2 times 1. and 2 times 1 is 2, so 2 plus 1 is 3, so we have 2/3, plus 2 divided by 2 squared, which is 4, plus 2 times 2, so we have 4 plus 4, which is 8, and so we have 2/8, right? So 2/8, but that's the same as 1/4, so I'm just going to rewrite that to be 1/4, and then we'll add that to 2 divided by 3 squared, which is 9, plus 2 times 3. 2 times 3 is 6, plus 9 is 15, and so we have 2/15. And then we could add on from there. But now looking at these terms, we can already see that it doesn't look like this series is a telescoping series. We don't have terms that are collapsing or canceling out. However, don't stop there. What we should try to do now is see if we can break up this rational expression into partial fractions. And maybe once we do that, we'll be able to identify this series as a telescoping series. And so let's do that. Let's take a look at our rational expression. If we want to break this up into partial fractions, we first need to factor the denominator. And note that both terms have n in them. And so we can pull that n out. And so I'll write 2 divided by n times n plus 2. Right? If we pull n out of n squared, we are left with n. And if we pull n out of 2n, we're left with 2. And so we now have two linear factors in the denominator, and so our partial fractions will look like this. We'll have a coefficient of a divided by the first factor of n, plus a coefficient of b divided by the next factor of n plus 2. And so once again, we want to solve for a and b, and then we can rewrite our rational expression with those two partial fractions. And so what we'll do is we'll set the numerator of the rational expression we want to break up equal to each of our coefficients multiplied by what they need in their denominator to have the common denominator. And so we'll have 2 is equal to a, and a has a denominator of n, but to have this common denominator, it needs n plus 2. So we'll multiply it by n plus 2. Then we'll add that to b, and b has a denominator of n plus 2, and so it needs n to have the common denominator. So we'll multiply b times n. And this is the equation that we will use to solve for a and b. All right, so let's start by solving for a. If we let n equal 0, we'll have 0 times b, and that will eliminate this term and let us solve for just a. B will no longer be in the equation. And so if we let n equal 0, we will have 2 is equal to a times 0 plus 2 plus 0. And so if we simplify, 2 will be equal to a times 2, and if we divide both sides by 2, we'll find that a is equal to 1. All right, so that's our first value. We found what a is, but now we want to solve for b, and so if we let n equal -2, that will make this factor 0 and eliminate a from the equation, right? -2 plus 2 is 0, and so that will make this whole term 0. So if we let n equal -2, then we will have 2 is equal to 0 plus b times -2, and that simplifies to 2 is equal to b times -2, and if we divide both sides by -2, we will have that b is equal to -1. And so once again, b is -1, and a is +1, and so if we replace those values for a and b in our partial fractions, we will complete our partial fractions and be able to rewrite our series. And so I'll erase a, and replace it with 1, and then erase b and replace it with -1, but we can pull that negative out front, and so we'll just subtract that fraction, and so we'll have -1 divided by n plus 2. And so now we have our two partial fractions that we can use to rewrite our series. And so if I clean up my work, we will have that this is equal to the sum from n equals 1 to infinity of 1 divided by n minus 1 divided by n plus 2. Okay, and so now we can look at the terms of this series, and we can decide if we have a telescoping series, and if we do, we can determine its convergence by using that nth partial sum. And so I'll clean up my work again here. Let's take a look at the nth partial sum, and we'll start by looking at the first term, a sub 1. And so for a sub 1, n is equal to 1, so we have 1 divided by 1, which is 1, so we have 1 minus 1 divided by 1 plus 2, which is 3, so we have 1/3. Then we'll add that to a sub 2 when n is equal to 2. So we have 1 divided by 2, which is 1/2, and then we will subtract 1 divided by 2 plus 2, which is 4, so we have 1/4. then we'll add that to a sub 3. And so when n is equal to 3, we have 1 divided by 3, which is 1/3. And then we will subtract 1 divided by 3 plus 2, which is 5. So we have 1/5. All right, now before we work on the next term, I just want you to look at what we already have here. It seems like we might have a telescoping series, but it looks a little bit different than what we've had before, right? We have 1 minus 1/3, but then the immediate next term is not positive 1/3. Positive 1/3 shows up later. So we do have terms that are canceling out, but not all of them. And so let's write out a couple more terms to see what's going to happen here. So let's work on a sub 4. And so if n is equal to 4, we have 1 divided by 4, which is 1/4. And then we will subtract 1 divided by 4 plus 2, which is 6. So we have 1/6. And so now with that term, you can see we have a positive 1/4 that will cancel out with this negative 1/4. And so it looks like everything's going to work out. But let's write out another term just to be sure. So we're going to add a sub 5. And so when n is equal to 5, we have 1 divided by 5, which is 1/5. And then we will subtract 1 divided by 5 plus 2, which is 7. So we have 1/7. All right, so now you can see that eventually most of our terms are going to collapse. Negative 1/3, positive 1/3, negative 1/4, positive 1/4, negative 1/5, and positive 1/5. So it seems like after 1 and 1/2, the rest of our terms are going to cancel. Instead of just being left with one term that doesn't cancel, we are now left with 2. And that's because of the denominators of our two fractions here. We have n and n plus 2, so it's going to take 2 terms until 1 divided by n is the same value as a previous 1 divided by n plus 2, if that makes sense. Right, our first 1 divided by n plus 2 was 1/3, but it took 2 more terms until we had a 1/3 to cancel out with that. And so the same thing occurred for 1/4. We have a negative 1/4 here, but then 2 terms later we have a positive 1/4. And so now we can skip forward a little bit. Let's go beyond a sub 5, and let's look at a sub n minus 4. And we're going to work our way up to a sub n. And so in this case, n is equal to n minus 4. So we're going to have 1 divided by n minus 4, and then we will subtract 1 divided by n minus 4 plus 2. So if we have n minus 4 plus 2, negative 4 plus 2 is negative 2. So the denominator is n minus 2. So we'll have 1 divided by n minus 2. Then let's do a sub n minus 3. And what we're going to have there is 1 divided by n minus 3 minus 1 divided by n minus 3 plus 2. So we have n minus 3 plus 2. Negative 3 plus 2 is negative 1. So our denominator is n minus 1. So we'll have 1 divided by n minus 1. And then we'll add our next term down here for a sub n minus 2. And so when n is n minus 2, we'll have 1 divided by n minus 2 minus 1 divided by n minus 2 plus 2. And so n minus 2 plus 2, negative 2 plus 2 will become 0. And so our denominator is just n. So we have 1 divided by n. Then we'll add this to a sub n minus 1. And then we'll conclude with a sub n. Right, the nth partial sum adds up all the terms until a sub n. Now for a sub n minus 1, we will have 1 divided by n minus 1. So we'll do 1 divided by n minus 1 minus 1 divided by n minus 1 plus 2. And so if we have n minus 1 plus 2, negative 1 plus 2 is positive 1. So we will have 1 divided by n plus 1. And then for our last term, we're just going to have 1 divided by n minus 1 divided by n plus 2. That's when n is equal to n. So we will have 1 divided by n minus 1 divided by n plus 2. Okay, so now let's look at all of our terms here and see what cancels out and what doesn't. We know that negative 1/3 will cancel out with positive 1/3. We know that negative 1/4 will cancel out with positive 1/4. Negative 1/5 will cancel out with positive 1/5. And then negative 1/6 is going to cancel out with a term later on that we did not write out, but it is going to cancel out like the rest of the terms. And the same thing is going to occur for negative 1/7. That will cancel out with some term later on that will have positive 1/7. And if we look at these terms here, we can see that negative 1 divided by n minus 2 will cancel out with positive 1 divided by n minus 2. Negative 1 divided by n minus 1 will cancel out with positive 1 divided by n minus 1. Negative 1 divided by n will cancel out with positive 1 divided by n. And so since both terms of a sub n minus 2 cancel out, we can then conclude that both terms of a sub n minus 3 and a sub n minus 4 will also cancel out. It's just that these two parts will cancel out with terms that we did not write. So that would be a sub n minus 5 and a sub n minus 6. If we did write those out, you would see that these two fractions also cancel out. And so both of those are going to cancel out with something in there. And now what we're left with is 4 terms. We're left with 1, 1/2, negative 1 divided by n plus 1, and negative 1 divided by n plus 2. All right, so none of these 4 terms are going to cancel out with anything within our nth partial sum. We are left with 2 terms from the beginning and 2 terms from the end. And so what we'll have is that s sub n, the nth partial sum, is equal to 1 plus 1/2. That's these first 2 terms, but we can combine them to be 3/2. So we're going to have 3/2 minus 1 divided by n plus 1. So we have 1 divided by n plus 1. And then we will also subtract 1 divided by n plus 2. And so that's the last part of our nth partial sum. This is all that's left after all of our terms collapse or telescope. Okay, so this is a little bit different than our previous examples. The terms that collapse were not right next to each other. They appeared later on within the terms, but they still collapsed at some point. But because of that delay, because of the difference between the denominators, we do have an extra term at the beginning and an extra term at the end that show up in our final s sub n that we didn't really see before in our previous examples. Okay, so just be aware that if your terms that cancel out are not right next to each other but appear later in other terms, your nth partial sum is probably going to include more than just the first term and the last term. You're probably going to have some other values that don't cancel. Okay, and so now if I clean up this mess here, we can determine the convergence of our telescoping series by taking the limit as n approaches infinity of our nth partial sum. And so if we do that, we will have that the sum is equal to 3/2. The limit of a constant is just the constant. And then we'll have minus the limit as n approaches infinity of 1 divided by n plus 1 minus the limit as n approaches infinity of 1 divided by n plus 2. Now for both of these limits, look what happens to the expressions as n approaches infinity. Both denominators, n is becoming larger, and then we're just adding 1 and 2 to each of them. So we just have denominators that are increasing towards infinity. And so in both cases, we have 1 divided by infinity, or an increasing value. And so a fixed value divided by an increasing value is always going to be 0. The limit as n approaches infinity of those expressions will be 0. And so we find that the sum is equal to 3/2 minus 0 minus 0, which gives us the final answer that the sum is equal to 3/2. And so 3/2 is the sum of this telescoping series, which means that our telescoping series converges to 3/2. And so that is the final answer for this example. Okay? And so with that, this is the last example for this video. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.